Hello class, the primary purpose of this video is just to give you a nice quick video that basically kind of goes over some of the basic motions. Please realize you don't have to know the speeds. Don't worry about memorizing the speeds and that stuff. That's just kind of crazy. I really just showed them here for like the cool effect. I mean, look at that. We're rotating at 1,000 kilometers per hour. That's pretty cool. We're orbiting the sun at 100,000 kilometers per hour. So please don't focus on that. What I want you to do is I just want you to focus on and know, okay, this is how we are moving. And these motions influence what we see in space. So here's what we're going to do. First thing you got to realize is you have to differentiate between rotation and revolution. Okay, that's one of the primary things. Of course, rotation is the spinning of the Earth, as being demonstrated here, spinning on its axis. You can see that we do have a 23.5 degree tilt of that axis, so we are not a perfectly vertical planet. But here's the interesting thing about this. To make one 360 degree revolution, it only takes 23 hours and 56 minutes to actually do that. Now, that's pretty interesting, and we're going to explain that in a later lecture. Then why do we have a 24-hour day? So don't worry about that right now. Just get down these basic motions and understand whenever you talk about rotation, we're talking about spinning on the axis. Whereas when you talk, whenever you start talking about revolution, revolution is the orbit around the sun. Now, let's go ahead and get this kind of out of the way there, kind of recognize some patterns that we see here. Please notice that axial tilt. That axial tilt remains constant. That's a big deal, okay? And notice that it takes 365.25 days. And please realize that we account for that, of course, every 4 years. What do? We add a day. We call that leap year, okay? Now, one of the primary things is because we have an elliptical orbit, we are actually closer to the sun at times than we are others. Now, you can't really see it in this because it is ever so minute. I mean, it's very, very close. It is only 5 million kilometers away, so you're not going to be able to see it. But what you're going to be looking at is, with our revolution, and this is going to really kind of be like, wow, we are actually closer to the sun right there in the winter solstice. In December and January, we are closer to the sun than we are in the summer. In the summer, we are at our farthest point, okay? So basically, whenever you start looking at that, you're being like, okay, these are our first two motions. These primary motions influence what we see in the night sky. That's what I want you to remember. Of course, you have two terms here. You have perihelion and aphelion. With any science class, you do have to recognize and understand vocabulary. So please make sure you understand perihelion, which is close. And then anytime you see a in front of any word, that means not. Okay, so it's not close to the sun. It's at its farthest point. Okay, so of course we are at aphelion in the summer and perihelion in the winter. Some of the other motions that we actually have is our solar system. Our solar system is actually moving through space. It's moving through the arms of the galaxy. Okay, and with that, which is really cool there, this is one of the cool diagrams I was able to get. What you can actually see there is that whenever you hear about what is called a cosmic year, that's 225 million years, and that's how long it takes us to get around the center of our galaxy. So that's a cosmic year, if you ever hear that. So it's kind of cool to see. Okay. And now with these other motions, don't really worry about this. This is going to be something that we talk about later. This one's going to blow your absolute mind because, yes, the stuff that we're moving through is actually expanding as well. Space itself is expanding. And then, of course, this kind of goes on into the observable universe and what's going on with this. Please don't, like I said, don't really focus on this. This was just something that basically, this is one of my favorite parts. So whenever you start talking about, where is the actual edge? Well, there is no actual edge, okay? Because if you look at 13.7 billion years away, that's the edge of our observable universe. Well, what about this galaxy over there? Well, now you've got to say from that galaxy, they're going to have a circle of 13.7 billion years. And then that circle actually extends out into this area. Well, why can't we see it? because we haven't had enough time for the light to get here yet. So the light has left these objects that are way out here, and then of course it's coming back towards Earth, and we just haven't seen the light yet. And what's really kind of cool about that is called Olber's paradox. Olber's paradox basically explains that. So really, there is no edge of the universe. There is an edge of the observable universe. Kind of crazy. Okay. And this video just kind of goes into the explanation of it. So like I said, this is a short video, but please know those motions and the differences between rotation and revolution, and kind of know how long it actually takes for each one to occur.